Alright, hi all, welcome back. Today's video we want to introduce the gradient. The gradient is something that's very important. You see it in physics everywhere. It is everywhere in physics. And it's also pretty much everywhere in mathematics. We get to introduce a new symbol, which we don't get to do very much. The last new symbol we had was the partial symbol. Now we get a new symbol. Anyways, the gradient is something, again, very important. It is one component of how we define the directional derivative, but it tells us a lot about our graph, and we're going to be using it a lot in the rest of Unit 3. So let's get started and discuss the gradient vector. So I'll derive this. So we start with the definition of the directional derivative, which says that the derivative in the direction of some unit vector u of some function f of x and y, I'm doing the two-variable case, is equal to partial f partial x times a plus partial f partial y times b. And we say this such that u hat is equal to the components a and b, right? Okay, so what we do now is you can tell that we have some derivative term multiplied by some constant term. So both of these could be written as a dot product. So we write it as a dot product. If we write it as a dot product, we get partial f partial x, partial f partial y, dotted with ab. And we can rewrite this as partial f partial x, partial f partial y times u hat. So we define this quantity of this vector with vectors with all of these partial derivatives. We define this as the gradient of f of x and y. You can use this upside down triangle symbol, which we call del, or you could call it the gradient, or you can call it nabla. In vector calculus, we use this symbol for a couple of other things, but we'll discuss that later on. But you can use the circle, so nabla f, that's gradient of f. Nabla is the LaTeX command for this upside down triangle. So if you do nabla slash nabla, you get the circle. You can also write it as grad of f, or grad of little f. But anyways, it's the same thing. But anyways, you can also write it in component form, such as partial x partial f partial x I hat plus partial f partial y j hat. Now let's bring this up to multiple variables. If I have a function of n variables, I want to take nabla f, x sub 1 all the way to x sub n, then that's equal to sum over I of partial f partial xi times e sub I, and e hat sub I, e hat sub 1 could be the x basis vector, I hat, e hat sub 2 could be the y, or could be the j basis vector, and then e hat sub 3 could be the k hat basis vector, and so on and so forth. We just use that e as some dummy variable for some sort of basis vector. Anyways, if I want to write that in vector form, I get partial f partial x1 all the way up to partial f partial xn. So that should be xi, that should be xn. Anyways, we can also use this to redefine the directional derivative, such that the directional derivative, d sub u f, is equal to the gradient of f times the unit vector u hat. Okay, let's try an example. It's very simple to do this because, again, what we've been doing, at least for the chain rule, for the directional derivative, for all of this stuff, we've just been applying partial derivatives. So we're just going to keep on going with that when we do the gradient. So let's say I want to find the gradient of f if f of x and y is equal to cosine of x plus e to the xy at 0, 1. Okay, so how do I do this? Well, what I do is I want to find my partial derivative. So if I find partial f partial x, I get negative sine x plus y e to the xy. And if I take partial f partial y, I get x e to the xy. We need to use the chain rule a little bit in there. Okay, Anyways, not the multivariable chain rule, by the way, just the single variable chain rule. Okay, let's keep going. If I want to find nabla f, then that's going to be negative sine x plus ye to the xy, and then my next component will be xe to the xy. And I want to find nabla f at 0, 1, so I just plug in 0 and 0 for all my x's and and 1 for all of my y's in this vector here. So I get that the nabla of f, or the gradient of f, at 0, 1 is equal to the vector 1, 0. Okay, so that's how we do the gradient. In the next video, I would like to discuss the gradient in more dimensions, and then we want to talk about optimization problems with the directional derivative, so how to maximize the directional derivative. And then after that, we are going to be moving on to our final topic well, not really our final topic, our second to final topic, which is going to be maxima and minima of these multivariable functions. All right, thanks for watching. We'll see you next time.